So the name of my talk is Hard Problems, Easy Solutions. And what I want to get across today is the fact that in statistical machine learning for biomedical big data, basically every problem is hard. But sometimes if we think about it, we can find a way around the hard problem that actually can be pretty easy. So biomedical research, of course, has really changed. It used to be that someone would spend a lot of time in the lab conducting a lot of very laborious, time-consuming experiments. And then at the end, there would be a little bit of statistics and data analysis. But today, the picture is really different. So of course, it takes time to collect data. There's a lot of experiment and lab works that go into it. But a lot of time is spent on statistics and data analysis, on computational pipelines, on machine learning to make sense of the data. And unfortunately, these analyses typically aren't very straightforward. So often, in order to make sense of our data, we actually need to develop new statistical methods, maybe because data of this scale really can't make use of existing statistical methods, or maybe because the questions that we want to answer are really new questions that weren't there before when we had smaller data. So I come bearing some bad news. And the bad news is that in terms of statistics, even problems that look really easy can actually be really hard when we have very big data sets. And to illustrate that point, I just want to look at a little case study. So this is a case study of graphical modeling for time course data. So what do I mean by this? Well, we have some data that looks like this. You can see in this plot, on the x-axis, there's time, and on the y-axis, there's a gene expression value. And we have 9 genes, each shown in a different color, measured over time. And what we want to do is take this data and end up with a picture like this. This is a graphical model. The graph has 9 nodes, 1 for each gene, and some of the nodes are connected by edges. And if there's an arrow or an edge pointing from one node to another, for instance, there's an arrow pointing from the first node to the 4th node, then that means that the first gene's expression regulates the 4th gene's expression. And what we want to do is be able to figure out where the arrows are. So the data is on the left. What we're trying to do is put together a picture like the one on the right. We need to know where the arrows go. So how do we actually do this? Well, we should start by understanding the data a little bit better. And so this is multivariate time course data. So what I mean is that at time 0, we measured the expression of a bunch of genes. Each gene is shown in a different color. And then we do it again at a later time point and again. So our data looks like this. But I'm a statistician, so it's not enough for me to have data. I need to have a model for the data. And I'm going to use a really simple model. And my model tells me that this data comes from some underlying trajectories that we actually don't get to observe. So the pale curves in this plot, they represent trajectories for each of the genes in my data. And it would be great if I got to see these underlying trajectories, but I don't. Instead, what I see are these trajectories measured at discrete time points, and at each time point, there's noise. So like at the first time point, I see these noisy observations, which are just these trajectories plus some noise, and similarly at the later time points. So I wish I could see those underlying trajectories, but I can't. I just have real-life data, which is noisy. So for instance, for a particular gene, we can call it gene J. There's this underlying trajectory, which is this pale curve. I'm going to call it xj. I don't get to see xj, but I do see xj plus some noise at a series of time points, and I'm going to call that yj. So similarly for this gene, there's an underlying blue trajectory, and I don't observe it, but I do see it with some noise added, and similarly for that gene, and so on. So what I need now is a model to couple all of the trajectories together. I need a model that allows me to tie together all of these underlying trajectories. And the way that I'm going to do this is really using the simplest model that's available to us for modeling temporal data. And this is an ordinary differential equation model. So what this model is telling me is that the change in expression in the jth gene as a function of time is just the sum over all of the other genes of some function of the other gene's expression values. So it sounds like a mouthful, but it's actually not too bad. Fjk is a function that tells me the extent to which the kth gene affects the jth gene's expression over time. So to make it really concrete, here's a little toy example with 3 genes. And if we look at the system of equations, we see that x1's expression is a function of x2, x2's expression is a function of x3, and x3's expression isn't a function of either of the other genes. So corresponding to the system of equations, there's a graph where there's an arrow pointing from x2 to x1 and an arrow pointing from x3 to x2. And this graph is just directly encoding the dependence among the genes that is on the equation on the left-hand side. So the problem is, nobody gave me the set of equations on the bottom left. I need to learn those from the data. Essentially, the issue is that those functions f, j, k are unknown, and I want to know which of those functions are 0 and which of them aren't 0, so that I know where to put the arrows in the graphical model on the right. So this is my model. And the first problem that we encounter as statisticians is that the FJKs are unknown. I don't know what kind of effect one gene's expression might have on another, and I don't want to have to make a lot of assumptions. But it turns out that statistically, that's actually not a big problem, because as statisticians, we're very comfortable making what's called a basis expansion, where we approximate this unknown function FJK using a set of known basis functions. This is the notation psi on this slide, and the details actually aren't too important. But what is important is that even after we make this approximation on the right-hand side, and now we want to estimate the theta JKs, because the theta JKs tell us if the kth gene affects the jth gene, we actually have a really big problem, which is that the x's are unobserved. Remember, the x's were these unobserved, noiseless trajectories. We don't see the x's. We see noisy realizations of the x's, which are the y's. So there's a pretty straightforward thing that we can try to do. We can try to use the noisy y's that we observe in order to estimate the x's, and then we can just fit the model on the top of this slide. So this is actually the approach that basically every method for this problem in the literature takes. So again, they're trying to fit the model on the top here. And the parameter of interest is theta jk. We want to know whether or not theta jk is 0, because that tells us whether we should put an arrow in our graphical model. The problem is we don't know the x's, and this model clearly requires us to know or at least be able to estimate x's. So what people do in the literature is they say, OK, I don't know the x's, but I do get to see the y's, which are noisy realizations of the x's. So I'm going to use my y's to estimate the x's. I'll call that estimate x hat. And then I'm just going to plug in that estimate of x on the right-hand side. So see now on the right of that equation on top, I have an x k hat, which is my estimate. I still need an estimate of the derivative of x. And in order to do that, I'm just going to take my estimate x k hat, and I'm going to differentiate it. So this is what essentially all the methods in the literature do. But unfortunately, this does not work well. And the reason is because statistically, it's really, really hard to estimate a derivative. So in this example, the derivative of x k hat is shown in blue, and the true derivative of x is shown in red. And what you can see is that those really don't look a lot alike. This is not just a weird artifact of this example. This is what actually happens, because it's really hard to estimate a derivative. My x hat might be pretty close to x, but the derivative of x hat is going to be totally different from the derivative of x, because any small amount by which my estimate of x is off is going to lead to a huge problem with the derivative. So existing methods are just directly making use of an estimate of a derivative, and that's just a really bad estimate. And so when they fit a model, they're basically putting in something that's not very accurate into the model, and as you might expect, the ultimate estimate of the graph that they get back is not going to be very good. So we thought about this problem, and we tried to think, is there a really easy way around it? Is there something simple that we can do to solve this problem? And so we used one of the simplest tricks that we have available to us in the mathematical sciences, which is calculus. And so we decided to just integrate both sides of the equation and rearrange the terms. So again, this is our ordinary differential equation model on the top. I'm just going to integrate both sides. I'm going to just do a little bit of algebra to rearrange some terms. And now my ODE model, my ordinary differential equation model, looks like this. And I still have some things I need to estimate, because I still need the xj's, and I need the integral of the xj's now. And once again, the x's are unobserved. So I'm going to do like I did before. I'm going to take the y's. I'm going to use the y's to estimate the xj's. I'll call my estimate x k hat. And I'm going to plug in y and xj hat on the top left. And there's still a quantity on the top right that I don't know. It's the integral of x. And what I'm actually going to do is I'm just going to take my estimate x hat, and I'm going to integrate it. And I'm going to treat that as my estimate of the integral of x. And it turns out that that estimate is actually spot on. So in blue, I have my estimate of the integral of x. And in red, I have the true integral of x. And you can see the difference between them is almost not distinguishable by I. My estimate of the integral is almost perfect. And the reason for this is that statistically, estimating an integral is really easy. In exactly the same way that estimating a derivative is really hard to do accurately, it's actually very easy to estimate an integral easily. Because if my estimate of x is a little bit off, when I integrate, I'm averaging out a whole bunch of tiny little inaccuracies in my estimate of x, because an integral is just an average. And the average of a whole bunch of little errors is actually not such a big deal. So what I've done is I've transformed a really hard problem that required estimating a derivative to a much easier problem that requires estimating an integral. And now that I have everything plugged into this equation, on the top here, I can now estimate the theta jk's and get a really accurate estimate of my graphical model. Much more accurate than I would have gotten if I had estimated the derivative in the way that existing methods do. So just to summarize, I start out with some data. This happens to be multivariate time course gene expression data. I encounter a problem, which is that derivatives are tough. I integrate. It's not that hard. It's an integral. And I end up with a much more accurate picture of the relationships among these genes than would have been possible if I had done the straightforward thing and just differentiated. OK, so there were a lot of details here. And this is just one example, but it's an example of a bigger picture, which is basically that as a statistician working in this area, every day I'm faced with really bad news, which is that things that look really easy turn out to be hard. I want to estimate a couple of parameters. Suddenly I'm estimating a derivative. It's a big mess. But then there's also good news, which is sometimes some of these problems that are really very hard end up having surprisingly easy solutions. So it's not always so easy as integrating instead of differentiating, but when we're lucky, it is. So thanks so much.
Thank you.